So let's dive into the problem. Okay. So the problem is that you have a sandwich of length n, and you want to divide it into as less parts as possible, such that no part exceeds length k. Okay. So basically, what you want to do is you want to give as many parts length k, so that the number of parts is minimized. Okay. So what we are essentially doing is we are taking modulo k, and the total number of parts we get would be seal n by k. Okay, cool. So if you didn't get this, please don't watch the video ahead. Okay, okay. So
offensive.
Okay, so this is the first part of the problem. The first part of the problem is that we have to find the minimum number of parts which we can obtain. So this will be the minimum number of parts we can obtain. The second problem is way more difficult than the first, and the second problem is that find the number of ways in which we can divide it into these many parts. Okay, so we have a sandwich of total length n. Okay, so this length is n, and we have to divide it into these many parts. Suppose this is r. We have to divide it into r parts. Okay, so suppose the first part has length x1, second part has length x2, goes on. The last part has length xr. Okay. So what we know is that the sum of all the values of x would be equal to n, because the total length of the sandwich is n. So the constraints on xi are that 1 less than equal to xi less than equal to k. That the maximum length of a part should be less than equal to k, and every part should have length at least 1. No part should be empty. Okay. So let us now define yi equal to k minus xi. Okay. So let's transform this equation to summation k minus yi equal to n. And what will be the constraints on y? So the constraints would be 0 less than equal to yi less than equal to k minus 1. Okay. When xi equal to 1, it is k minus 1. When it's k, it's equal to 0. Okay. So we have to find the number of solutions of this equation. Okay. So we can transform this to I equal to 1 to r. So we can transform this to summation I equal to 1 to r. Why I just take this to the right side, it would be kr minus n. Okay, and the constraints are 0 less than equal to yi less than equal to k minus 1. Okay, so now notice that the value of the right hand side, which is k into r minus n, has to be less than equal to k minus 1. Okay, because r equal to seal n by k, which is equal to n by k minus fractional part n by k. Okay. So now notice that the right hand side has to be less than equal to k minus 1. This is because r equal to seal n by k, and k into r minus n equal to k into seal n by k minus n, and so suppose if n is equivalent to, suppose if n is equal to k into I plus j, then we write the right hand side is k into, so this would be, so the first case is when j is equal to 0. When j is equal to 0, then k into n by k would be the same as n by k, because it's totally divided by k, n is totally divided by k, and this would be 0, okay, which is definitely less than equal to k minus 1. So we are considering a case when j is not equal to 0. Okay, so this would be equal to, and where 0 less than equal to j less than k. Okay, so the right hand side is equal to, the seal would be equal to I plus 1, k into I plus 1 minus n, and n equal to k into I plus j. So this would be equal to k minus j. And now we already said that if j equal to 0, then we were done. So j is not equal to 0, and the right hand side would be less than equal to k minus 1. Okay, the 0 case is already handled. In the 0 case, it would not be, the CL would not be equal to k into I plus 1, it would be k into I instead. Okay, and then the RHS would be 0 instead. Okay, so we have proved that the right hand side is now less than equal to k minus 1, and the constraints on the variables is also less than equal to k minus 1. So even if we make the constraints to infinity, it does not matter, because they would never yield a feasible solution. Because if some y is greater than k minus 1, it's still valid, because it would not add to the number of solutions, because it can't be a feasible solution if some y is greater than k, because the right hand side is already less than k. Okay, so we can say that we can remove this and put an infinity here, and this is a pretty standard solution whose solutions we already know. The number of solutions of this would be equal to kr minus n plus r minus 1, choose r minus 1. This is a pretty standard solution. This is a pretty standard equation we come across. The number of integral solutions of an equation, summation xi equal to n, I equal to 1 to r, and such that 0 less than equal to xi less than equal to infinity. So the number of solutions of this equation is given by n plus r minus 1, choose r minus 1. Okay. So we get the number of solutions as kr minus n plus r minus 1, choose r minus 1. So we have to evaluate this value modulo some n which we are given. Okay. So we have to, our task is to find this mod n. Okay. So the constraints now are k comma n less than equal to 10 to the 18. So these are pretty huge. We can't have a linear solution here. So we have to think of something different. So how do we find out this modulo? Okay. So let us try to solve the problem n choose r mod m, where these constraints are order 10 to the 8, where 10 to the power 18. So let's try to solve. So let us first solve this problem. Okay. So we are given n and r, and we have to find n choose r modulo p to the e. Okay. So we have to find NCR mod p to the e. Okay. Now we know the constraints of n and r. And we also know the constraints on p to the e. Right? Okay. So these are the constraints, and we need to find out n choose r mod p to the e. Okay. So we know that NCR equal to n factorial divided by r factorial into n minus r factorial mod p to the e. Okay. Cool. So we have to find out this. Okay. So let us define some functions first. So let's say that g of I equal to 1 if p divides I and I otherwise. Okay. So the point is, if p divides I, then g of I is equal to 1, and if p does not divide I, then g of I equal to I. Okay. So let us define this another function. Say f of I is equal to product of all numbers less than equal to I which are co-prime to P. Okay, so we are finding the product of all the numbers which are less than equal to I, but we consider only those which are co-prime to P. So say if P is equal to say 7 and I is equal to 10, then f of I would be 1, 2, 3, 4, 5, 6. But we don't consider 7 because 7 divides 7. Okay, so 7 and 7 are not co-prime to each other, but we have to consider only those numbers less than or equal to I which are co-prime to P, or the numbers which P does not divide. So we won't consider 7, we would consider 8, we would consider 9, and we would consider 10. So f of I equal to this. Okay. So we can say that f of I equal to product of all j from 1 to I g of j. Why? See, in j from 1 to I, if some I is not co-prime to P, we do not have to consider that. But if some I is not co-prime to P, then P divides that number and g of that particular number would be 1. So that is like we did not consider that number. So we are considering only those numbers which are co-prime to P in this case. Okay. So f of I is equal to this. We can say that. Okay. So let's say that. Now let's define h of I. H of I equal to I divided by P to the power R, where R is the maximum power such that P to the R divides I. So basically R is the power of P in the prime factorization of I. From I we extract the power of P, and that number would be Hi. Okay. Okay. Also let's define En comma P is equal to exponent of P in n factorial. Okay. And let us also define f of n equal to n factorial divided by P to the power E n comma P. Okay. So again, what we are doing is we extract the power of P from n factorial, and that thing would be f of n. So now notice that P does not divide f of n because we have already extracted all of the power of P from n factorial. Okay. So now P does not divide f of n. Or in other words, P and f of n are co-prime to each other. Notice that if n is less than P, then this is a very trivial problem, because then if n is less than P, it implies that R is less than P and n minus R is less than P. Okay. Then R factorial has no power of P because R is less than P. So in product from 1 to R, P never comes. Similarly, n minus R factorial is co-prime to P, and so R factorial, n minus R factorial is co-prime to P. Okay. This means that the denominator is co-prime to P, and since it is co-prime to P, it is also co-prime to P to the E. Okay, so we can do it in a very trivial method when we take inverse of the denominator and multiply the numerator and just give the answer. Okay, but see, if we see the constraints, n can be greater than P. Okay, so the real problem is when n is greater than P, what should we do? Okay, so what we want to do is we want to make the denominator co-prime to P, because the problem is when the denominator is not co-prime to P and we are unable to take inverse. Okay, so what we do is we extract all the powers of P from the denominator, we extract all the powers of n from the numerator, and then we multiply with that particular power. Okay, see, we know that by Legendre's formula we can find the exponent of any prime in a factorial. Okay, so we can find the exponent of P in n factorial, we can find the exponent of P in R factorial, and we can find the exponent of P in n minus R factorial. So we can find the exponent of P in this product. Okay, and then the remaining part of the denominator would be co-prime to P, and we can do it in a similar fashion when you take inverse of the denominator, multiply by numerator, and give the answer. Okay, so let's define some functions. So Fn is equal to n factorial by p to the power e of n comma p, where p is the maximum power of where e of n comma p is the maximum power of p in n factorial. So in some sense we are extracting p from n factorial, and that result is f of n. Okay, so let's try to find f in terms of h. So notice that what h was doing is it was extracting all the powers of a prime from a particular integer. Okay, so we can say that f of n equal to product I equal to 1 to n h of I. Why? Because in h of I we are considering only that part which does not contain p. So remember that h of I equal to I divided by p to the e, p to the say something else, q, where q is the maximum power of p which divides I. So in some sense we are extracting prime p from I. Okay, so we are removing this prime so that the remaining part is actually co-prime to p. So when we have to find n factorial with p to the power e of n comma p, we have to remove all the powers of prime p from f. Okay, so what we do is we take the product of h instead of I. Notice that f was n factorial would have been the product of i's, but from all the i's we removed the powers of p, which is q for a particular I. So what is remaining is the product of all the numbers, such that we have removed the powers of p from them, which is exactly what we wanted here. Okay, so let's try to find f of n, small f of n. So how do we find small f of n? Remember that small f of n was the product of all numbers which are less than equal to n and also co-prime to n. Okay, so let us first make some observations about g. Okay, so I claim that g of I is the same as g of I mod p to the I modulo p to the I. Okay, so remember the definition of g. It was that g of I equal to 1 if p divides I and I otherwise. Okay, so there are two cases here. Case 1 is that p divides I. So if p divides I, then p also divides I modulo p to the e. Okay, and then both g of I and g of I mod p to the e are found. And the second case is when p does not divide I. In that case, p would not divide I mod p to the e, and in that case, gi and g of I mod p to the e would be equal, because I is equivalent to I mod p to the e modulo p to the e. So we say that g of I is the same as g of I mod p to the e. Okay, now f of n was the product of all gi's less than equal to n. Okay, so but now let us notice the repetition here. What is happening is, if we divide n into blocks of size p to the e, then let's say that this is the first block of size p to the e, this is the second block of size p to the e, this is the third block. So this starts from 1 and ends at p to the e, this starts with p to the n plus 1 and ends at 2p to the e, this starts at 2p to the e plus 1 and ends at 3p to the e, goes on. This last block which ends at n and starts at some k into p to the e plus 1. Okay, so firstly the product of any of the two blocks is the same. Why? Because at 1 the value is the same as p to the e plus 1. Why? Because of this, g of I equal to g of I plus p to the e. Okay, so at any I, g of I is same as g of I mod p to the e. So at 1 it's the same as this, at 2 it's the same as this, at 3 it's the same as this, and at p to the e it's the same as 2p to the e. Okay, so if we consider any two blocks, their values are the same. Okay, so now consider the last block. Okay, the last block starts at kp to the e plus 1 and ends at n. Okay, so the product of the last block is g of k p to the e plus 1 to g of n. Now this is the same as g of 1, and this is the same as g of n mod p to the e. Okay, so this is the same as g of 1, g of 2, g of n mod p to the power e. Okay, so this is the same as f of n mod p to the e. Remember the definition of f? It was the product of all the numbers which are less than or equal to n and co-prime to p. Okay, so the product of the last block is equal to f of n mod p to the e, and product of any other block is, so if we consider any other block which starts at some k dash p to the e plus 1 and ends at some k dash plus 1 p to the e, then we have all the numbers from 1 to p to the e, and their products would be g of k p to the e plus 1 to g of k dash plus 1 p to the e, and these are like modulo, because g of I is same as g of I mod p to the e modulo p to the e, then we say that this is same as g of 1, this next one will be same as g of 2, and this is the same as g of p to the e. So this is the same as f of p to the e. Okay, so overall, how many blocks are there of which are of size p to the e here? There are n by p to the e such blocks, because we are dividing n into blocks. Okay, and the last block has size n mod p to the e. Okay, so so what will be the overall product which we have to find? It would be f of n is equal to f of p to the e to the power n by p to the e into f of n mod p to the e. Okay, because the product of the last block is this, and product of any other block is this, and there are n by p to the e such blocks. Okay, so overall fn would be equal to f of p to the e into n by p to the e into f of n mod p to the e. Okay, so now notice that if we have f calculated for all numbers less than or equal to p to the e, then we can find out f of n in time order log n. Why? Because we know this value and we know this value, and we have to find power n by p to the e, so which is done by exponentiation, which is order log n in time. Okay, so to find f of n in order log n, we pre-compute all the values from 1 to p to the e in order p to the e, and then we can find this in order log n and this in order 1, and then we can just multiply to get the result fn. Okay, so notice that p to the e, the constraint on p to the e is p to the e is less than or equal to 10 to the 6, so we can easily pre-compute all the values from 1 to p to the e, all the values of f from 1 to p to the e in order p to the e. So let's see how to do that. Okay, so we know that f of n equal to product I equal to 1 to n g of I, and g of I equal to 1 if p divides I, and I if p does not divide I. Okay, so now it's fairly simple to calculate fn if we know the value of fn minus 1, because fn equal to fn minus 1 into g. Okay, so we can pre-compute the value of f from 1 to p to the e in order p to the e. Why? Because if we know f of n minus 1, we can find f of n from that. So we can just traverse from 1 to p to the e, and then using the previous value we can find the next value by just multiplying by g of that value, and finding g is very simple. We will just have to check if p divides I or doesn't divide. Okay, so once we have all the values from 1 to p to the e, we know this, we can multiply them and find answer. Okay, so now let us see how to find capital F of n using small f of n. Okay, so to find capital F of n, we divide our numbers from 1 to n according to the maximum power of p which divides it. So like for example, if p is 3 and like n is 10, and we have these numbers 1, 2, 3, 4, 9, 10. So we divide them according to the maximum power of p which divides them. So 1 is co-prime to P, no power of P divides it. 2 is again co-prime to P. 3, the maximum power of P which divides 3 is 1. Then 4 is again co-prime to P, 5 is co-prime to P. Again the maximum power of P which divides 6 is 1. So we write that in square. Then 7 is co-prime to 3, 8 is co-prime to 3. But now the maximum power of 3 which divides 9 is 2. So we circle this, and 10 is again co-prime to 3. Okay. So we divide the numbers according to the maximum power of P which divides them. Okay. So let's focus on one such group. Okay. Let's focus on a group where the maximum power of P divides the number is R. So let's use this notation. P to the R double divide. So double parallel arrow n. If this means that R is the max power of P such that P to the R divides n. Okay, so this is like double divides means that it's the maximum power which divides n. Okay, so so if we consider one such R, then what will be these numbers? P to the R into 1, P to the R into 2, P to the R into P minus 1. But now we won't take P to the R into P, because for that the maximum power would be R plus 1. Okay, so the next number we would take is P to the R into P plus 1. Goes on. So notice that we are taking those numbers, we are taking the numbers P to the R into X, where X is co-prime to P. Because if X is not co-prime to P, then there is some power of P which divides X, and then the total power of P which divides P to the R into X would be something greater than R, not R. Okay, so but if X is co-prime to P, then there is no power of P which divides X, so the maximum power of P which divides P to the R into X would be R itself. Okay, so we consider all those numbers which are of the form P to the R into X, where X is co-prime to P. Okay, so for these numbers, so what we are trying to do is we are trying to remove P to the R from these numbers. Why? Because that was the motive, to extract the power of P from the numbers and then find the product, so that the denominator is co-prime. Okay, so we have to multiply X for all these numbers. Okay, now notice that X is less than equal to n by P to the R, right? Because P to the R into X is less than equal to n, because we are only considering numbers in the range 1 to n. Okay, and for all these numbers we have to multiply X, so we have to multiply 1, 2, 3 goes on till n by P to the R, but we have to multiply only those which are co-prime to P, because that is how we have defined this. Okay, so the product of such numbers would be equal to f of n by P to the R, right? Because that was the definition of f. F means that the product of all such numbers which are co-prime to P. Okay, with all such numbers less than equal to n which are co-prime to P. Okay, so this is equal to f of n by P to the R. So for one particular R, we found that the product which is contributed by these numbers, which are of the form P to the R into X, such that R is a maximum power which divides this number, the contribution is f of n by P to the R. Okay, so for all such R this is true. Okay, so we divide the range 1 to n in according to the R of that number, and accordingly we find the contribution for all such groups and then multiply them. Okay, so for one such group the contribution to the product is f of n by P to the R. So for all such groups we can say that the total contribution is equal to product over R f of n by P to the R, and R is greater than or equal to 0. Notice that when R is equal to 0, then we have to find the product of only those numbers which are co-prime to P. Okay, when R is 1, we have to find the product of numbers which are co-prime to n by P, which are co-prime to P and less than or equal to n by P. Okay, so in such a fashion we can find f of n if we know small f of n. Okay, in the previous section we showed that f of n can be found in order log n time, So f of n can be found in order log n time now. Okay, so and we know that r is also order log n at max because the maximum power because then the maximum power of r, which is less than equal to n, is of order log n, right? So maximum power of p which is less than equal to n is order log n. Overall we can find fn in time order log square. Okay, so now let's come back to the original problem. We have to find this mod p to the e, right? So we write, so now we know that n factorial, so we know that f of n is equal to n factorial by p to the power e n comma p. Okay, so we can write this as f of n into p to the power e n comma p divided by f of r into p to the power e r comma p into f of n minus r into p to the power e n minus r comma p, right? And now we can take the powers of p separate and we can say that this is the same as p to the power en minus er minus en minus r, okay, into f of n, f of r into f of n minus r. Now notice that the denominator is now co-prime to p because we have extracted all the power of p here, right? So now this is co-prime to p and we can just find its inverse and multiply by the denominator to find the value of NCR modulo p to the e. Okay, and also we already showed that capital Fn can be found in order log square n, so can this and this. So overall complexity of this is order log square n. Okay. So now we know how to find NCR mod p to the e in order log square n time. So how to find NCR mod m, where m is less than or equal to 10 to the 6. 10 to the 6. How do we find this? Okay, so first of all we can prime factorize m is equal, say it is equal to p1 to the e1, p2 to the e2, pk to the ek. Okay, so now we can find the value of NCR mod p1 to the e1, mod p to the e2, and mod p goes until mod pk to the ek, and then we can use Chinese remainder theorem to find out NCR modulo the product of these. Okay, so there is a link in the description if you want to learn about Chinese remainder theorem. Okay, so yeah, if we have the values of NCR modulo pi to the ei, we can find NCR modulo m using Chinese remainder theorem. Pretty simple stuff, right? Okay, so that's it for this problem. I'm sure you found it pretty simple. So jokes apart, if you have any doubts, you can leave them in the comments. And I have left all the descriptions as I told in the beginning of the video below. So check them out. Thank you.